Hello there, in this video we're going to introduce a second set of ionic reactions. These include elimination reactions. By the end of this chapter, you'll come to realise that reaction pathways are dependent on an understanding of the substrate, the nucleophile or base that's involved, the substrate's leaving group, and solvents. Organic reactions are not always clear-cut, and competing reaction pathways are possible. Whilst I will be introducing you to a new set of reactions that involve the formation of a double bond, I will also be recapping and ultimately comparing competing reaction pathways between SN1, E1, SN2 and E2. Lastly, we'll be building on our retrosynthetic strategies towards target molecules, whilst also revisiting previous chapters. This lecture will be broken down into 4 videos. The first video A explains the mechanism of unimolecular elimination reactions, or E1, and details the factors that favour this reaction pathway. The second video B does the same thing, but for bimolecular elimination, or E2 reactions. In video C we will have a look at some examples of competing reaction pathways and how to consider the factors in turn. Lastly, in video 4, this is D, we will have a focus on some synthesis and retrosynthetic strategies towards a desired product. An elimination reaction involves a single substrate reacting with a base. In this example, a molecule of HBr, or hydrogen bromide, is eliminated from the substrate, resulting in the formation of a double bond. But as you can see, elimination can result in a mixture of products. Our aim is to understand the mechanism by which this reaction proceeds, its intermediates or transition states, and the resulting regio and stereochemical outcomes. However, before we begin, let's consider some more terminology that will aid our understanding throughout these discussions. In order for the possibility of an elimination, irrespective of following an E1 or E2 pathway, there are some structural requirements. Some of these are familiar, as they are the same for either an SN1 or an SN2 reaction pathway, but others are unique to elimination. The first structural requirement is that the substrate contains a hydrogen atom that is beta to an alpha carbon. This is unique to elimination. Second, the alpha carbon needs to contain a good leaving group, and this is similar to substitution. For E1, weak bases will be sufficiently strong enough to remove a hydrogen atom from the beta carbon, and in so doing will form a conjugate acid of that base. However, for E2, a strong base will be required. Lastly, here is some more terminology. A process that involves specifically the removal of a hydrogen and halogen atom is called a dehydrohalogenation reaction. Let's now take a look at the first mechanism of elimination, known as the unimolecular elimination pathway, E1. E1 should look incredibly familiar in terms of the rate determining step, as this starts in exactly the same way as the SN1 reaction mechanism. This is with the heterolytic cleavage of the alkyl halogen bond. An intermediate is formed like before in SN1, except the second step is where the base now has a choice, either to attack a carbon or a hydrogen. Acid-base reactions are typically faster. A weak base is sufficient enough to affect the abstraction or the removal of the proton. All of this happens in 2 steps. This is very similar to the SN1 reaction. SN1 products will always be a competing reaction pathway and accompany the formation of any E1 product. The rate determining step of an E1 reaction is going to depend on the stability of the carbocation formed. Sound familiar? The more stable the carbocation and the better the leaving group, then the lower the free energy of activation. All of this should be reminiscent of SN1. Now, let's look at the difference in the fast step. In the second step, a weak base will be more than sufficient to abstract the beta hydrogen, as these are very acidic. Energy will be released through the formation of a pi bond. Now let's take a look at the reaction profile for an E1 reaction. Again, this should look incredibly familiar, and while I don't have any cat analogies for this reaction, there are still the same features: 2 transition states, 1 intermediate, and the formation of lower energy products. The reaction rate of this reaction is always going to be concerned with the factors that lower the activation energy of the rate determining steps, i.e. the formation of the first transition state. See if you can draw such a transition state for the largest activation energy. See if you can also draw the intermediate. Pause the video and resume when you have an answer. Here is the transition state for such a reaction. It should come as no surprise that this is exactly the same transition state as for the SN1 reaction. Also, the intermediate is going to be exactly the same. The only difference is that in the elimination reaction, a beta hydrogen is removed and there is the formation of an alkene. So, what does the rate of this reaction depend on? The rate of an E1 reaction, like SN1, depends only on the substrate's identity. So like before, the choice of leaving group and the degree of steric hindrance around the reacting carbon center impacts on the rate of this reaction. Here's a reminder of some of the best substrates that you can use. Tertiary and secondary substrates, though these ones are certainly not ideal, are capable of E1 reactions. The stabilizing factor for forming the carbocation is down to the number of alkyl groups that surround the central carbon. When talking about elimination, we refer to this carbon as the alpha carbon. Tertiary and secondary carbocation intermediates, though the secondary ones will probably rearrange, are stabilized through hyperconjugation, just as they are for SN1 reactions. Hence, tertiary carbocations will always form more quickly than secondary and then primary, and this affects the rate of reaction. When there is the possibility of either a cis or a trans alkene being formed via E1, then the carbocation can adopt 2 conformations which are capable of undergoing elimination. So there is the less stable syn conformation, but there is the more stable anti-conformation. And so this is the one that will lead to the trans product. And if we see here, the trans product places the larger groups on either side of the double bond, that is, they're opposite to each other, whereas a cis alkene places the 2 large R groups close to each other, and this causes steric hindrance, and we know this to be unfavourable. In summary, the rate of an E1 reaction depends only on the substrate, since the rate limiting step is also the formation of that carbocation. Hence, the more stable that carbocation is, the faster the reaction will be. Elimination reactions have greater free energies of activation than substitution reactions because more bonding changes occur during the elimination process. And as such, when higher temperatures are used, the proportion of molecules able to surmount the energy of activation barrier for elimination increases much more than the proportion of molecules able to undergo substitution, although the rate of both substitution and elimination are increased by temperature increases. Furthermore, elimination reactions are entropically favoured over substitution because the products of an elimination reaction are greater in number than the reactants. Additionally, because the temperature is the coefficient of the entropy term in the Gibbs free energy equation, then any increase in temperature further enhances the entropy effect. Finally, there's no requirement for the stereochemistry of the starting material. The hydrogen can be at any orientation to the leaving group in the starting material. There is a requirement, though, for E1 that the carbon-hydrogen bond be able to rotate so that it's in the same plane as the empty p orbital on the carbocation when the new pi bond is formed. This results in the trans product.
This concludes part A.
In this video, we're going to be studying the E2 reaction mechanism, Just like SN2, this reaction relies on a concerted process in which a transition state forms fleetingly. The difference here is that this involves a very specific conformation of the base and the substrate. The reaction occurs in a single step, just like SN2. Here is the reaction coordinate for E2. Note again the similarity to SN2, and just like that reaction, the largest barrier to the E2 reaction is the formation of its transition state. And just like before, this transition state cannot be isolated. So what does the rate equation look like? What does this rate of reaction depend upon? Let's take a look. You can see the similarities between this rate law and that of the SN2 reaction. There are some subtleties which we will now consider that are unique to the E2 reaction, but just like before, let's now consider the substrate first and then look at, this time, the base. We'll make the assumption that the molecule has a good leaving group, and now this gets us to think about the R groups and their interaction with that base. The success of an E2 reaction depends ultimately on the conformation of the transition state. So this means there has to be the right alignment of atoms. Now this is similar to the situation with SN2, whereby the approach of the nucleophile has to come from a particular direction. However, the base this time needs to be able to successfully abstract, that's remove a hydrogen atom. This happens most favourably when there is an anti-periplanar arrangement of the atoms forming the transition state. This is seen here. Experimentally, the reaction has been proven to proceed via an anti-mechanism, and this is based upon two arguments, a steric argument and a molecular orbital argument. In this reaction, the sp3 carbon-hydrogen sigma bond contains a pair of bonding electrons. As the base approaches the hydrogen atom, the leaving group X leaves, taking the pair of electrons with it in a concerted process. The molecular orbital argument here is that the carbon-hydrogen sigma bond is in the right orientation to overlap with a sigma star anti-bonding orbital of the carbon leaving group. Now this can only happen if the orbitals are parallel, and this necessitates the anti-periplanar arrangement. Secondly, the steric argument places the groups in a more energetically favourable staggered conformation. We'll see this on the next slide. Ordinarily, the eclipsed syn-periplanar alignment also aligns the two sigma bonds that become the pi bond, but this is less favourable than the anti-periplanar arrangement. Again, this can be rationalised in terms of forming a cis compound, which will result in a sterically hindered alkene. So if this product is formed, it will be a minor product. The more stable conformation will always try to place the leaving group in an anti-periplanar arrangement, and this produces the more stable trans isomer. This is a little more advanced, but if you can follow this through, then it will allow us to tie together what we've discussed about E2 with what you've previously learned about cyclohexane chair flips. The first thing to note here is that the bromine in the left conformer is not in a periplanar arrangement with any of the hydrogen atoms. So as a result, this conformer would not be able to undergo E2. In order for this to work, bromocyclohexane has to undergo a ring flip. When this happens, the bromine and the hydrogen atoms highlighted are all within the same plane, that is, they are anti-periplanar and can adopt the transition state previously discussed. Here is the same example, but with the arrows shown for the developing bonds being broken and formed. This leads to cyclohexane. The most important take-home message here is that the hydrogen and the leaving group must have an axial arrangement of atoms. Here we have a di-substituted cyclohexane, and one of those substituents happens to be a halogen. In order to understand how E2 is going to progress, then we need to draw the cyclohexane chair forms for both of these molecules. In the top molecule, the left-hand conformation is favoured, and this is because the bulky methyl group, and yes, it's bulkier than bromine, is equatorial. So the equilibrium will favour the left-hand conformer. But in the bottom molecule, the right-handmost conformation is favoured because the bulky methyl group is equatorial. So equilibrium will favour the right-hand conformer. Notice something interesting? Remember that in order for E2 to occur, the leaving group must be axial. So there's only one conformation where this will be possible for each ring. However, in the top example, bromine is axial in the least stable conformation, whereas in the bottom example, bromine is axial in the most stable conformation. Since the bottom example will have a higher concentration where bromine is axial, this will be faster than the top molecule, and so more E2 will occur via this route than by the top example. The other factor that affects the rate of an E2 reaction is the use of a particular base or nucleophile. Now, the type of base you use will influence the rate of reaction. Also, if you use something that behaves as a better nucleophile than as a base, you will also have to start thinking about competing reaction mechanisms, i.e. whether the reaction is more likely to undergo SN2 than E2. In this section, steric effects also play a role in the ability of the base to gain access to a hydrogen atom, and this will affect the regioselectivity of the reaction. We will be comparing small unhindered bases with large bulky bases or hindered bases. Let's take a look at this now. If we consider the following reaction, there are actually two sets of hydrogens that are beta to the alpha carbon. Now, methoxide is a strong base. It has a negative charge, but it's also very small, and this means that it can approach the beta hydrogen that is in the antiperiplanar position of cyclohexane with ease. As a result of the concerted removal of the leaving group, a double bond is formed as shown, and this gives a product known as Zaitsev's product. These products normally consist of the formation of the more substituted alkene, which is more stable. We'll be focusing in on this again in a later lecture. However, what would happen if we used a strong base, but the base itself is sterically hindered? This hindered base is called potassium triethyl carbinolate, but there are plenty of others that are suitably hindered. Lithium diisopropylamide, 1,8-diazer-bicycloundex-7-ene, or DBU, potassium tert-butoxide. Normal bases are also nucleophiles, but often chemists seek the proton-removing ability of a base without any other function. Typically, non-nucleophilic bases are bulky, such that hydrogens can attach to the basic center, but any substitution reaction is completely inhibited. There is no way that these bulky bases can get anywhere near the axial hydrogens on this cyclohexane ring, because this would lead to steric hindrance, as shown. However, if the methyl group is expanded, it is possible for hydrogen abstraction to occur on these hydrogens that are pointed away from the ring, but are also in an axial position. This will form a less hindered alkene, i.e. one that is not as substituted. These are known as Hofmann products.
This concludes Part B.